Hello and welcome to Module 3, Concept Generation, Functional Analysis, System Architecture, and Design. In this module here, we will talk about system architecture. First of all, it should be clearly understood up front that the term functional architecture only describes the hierarchy of decomposed functions and the allocation of performance requirements to functions within that hierarchy. We will not be describing either hardware architecture or software architecture of the system. Those architectures are developed during the system synthesis phase of systems engineering. Look back at the Boyd-Ideffa model for the development of functional architecture. Starting in the upper left, under Create Simple Functionalities for Operational Concept. This creates many functional sequences or simple functionalities that satisfy the scenarios of the operational concept. Functions that are needed to transform system inputs into system outputs. From there, you then draft and evaluate a functional model. This synthesizes simple functions into a functional decomposition. Either a top-down decomposition or bottom-up aggregation is acceptable in this approach. Let's compare decomposition versus composition. First of all, the distinction should be made that decomposition is considered top-down, while composition is bottom-up. In a decomposition, you have a partitioned system function a level at a time, and you need sound definition of all inputs and outputs. Conversely, in a composition, you define many functionalities, bottom-level functions, and then synthesize functional hierarchy from the many bottom-level functions. Use of both of these is the best solution, the middle out. Going back to the Boyd-Ideffa model for the development of functional architecture. From draft and evaluate functional model, the flow of inputs and outputs from the outside of the system are then added. Data or items that serve as inputs or outputs of the various functions of the functional architecture, so that the relations among the various items flowing through the system are understood. Then complete functional and data models. At this point, make sure to solicit the opinions of other engineers and stakeholders. Consider missing functions, alternate decompositions or alternate functional architectures, feedback, or anything else that they may be able to provide. Also look at the physical architecture how it is proceeding, as well as the allocation of functions to the physical architecture. Feedback here could result in changes to the functional architecture. Then we conclude with tracing the input and output requirements. Now let's talk about physical architecture. In moving on to physical architecture, this provides the system resources to provide functions, including hardware, software, facilities, people, and procedures. Generic physical architecture is considered a description of the partitioned elements of the physical architecture without any specification of the performance characteristics of the physical resources that comprise each element. Instantiated physical architecture, conversely, are the generic physical architecture to which complete definitions of the performance characteristics of the resources have been added. Here is an example of physical architecture for the F-22 weapon system. The F-22 was created by Lockheed Martin as a small stealth military aircraft. At the top row, the weapon system is broken down into vehicle, training, and support components. Further subsystems within the vehicle components include avionics systems, utilities and subsystems, the cockpit and vehicle management system. Each of those could be broken down yet further, as shown by taking the avionics system down here. The full physical architecture would be much larger, of course, but this gives you an idea of what it would eventually look like. Here is another example of physical architecture, this time using just an elevator. Starting with the elevator system at the top, you could then break it down farther. Moving along just one path into the elevator car and shaft improvement, then into the shaft switch, and eventually the floor stop components. Note that while they look slightly different in structure, the form and concepts are still essentially the very same. This is the development process for physical architecture. Note that it looks very similar to that of functional architecture, if not being just slightly simpler. The first starting point is with brainstorming and selecting a generic physical architecture. Once the concepts are identified, the next steps become to draft and refine the physical architecture, finalizing by selecting the instantiated physical architecture. There are many techniques for brainstorming different options. There are so many ways to go about it, and this often depends on the preferences of the individuals or the organization at play. Here we have examples of brainwriting or brainstorming. The difference being brainwriting is an activity where you silent and write things down, whereas brainstorming is usually a very open-ended discussion with a group of people. Neither approach is right or wrong, and any one of these approaches listed here could be very successful for your organization. At the same time, while these are commonly used within the business, there are many other perfectly acceptable methods in which to conduct brainstorming. Let's conclude today by talking about some system and architecture terms that are used today. Robustness characterizes a system's ability to be insensitive towards changing environments. A robust system delivers the intended functionality under varying operating conditions without being changed. That is, no changes from external to be implemented into such systems to cope with changing environments. As a general rule, the more robust the system, the better it is perceived to be. Flexibility represents the property of a system to be able to be changed easily. Changes from external have to be implemented to cope with changing environments. Again, the more flexible, the better. Agility represents the characterizations of a system's ability to be changed rapidly. Changes from external have to be implemented to cope with changing environments. Similar to flexibility, however, the time element is being involved. And adaptability characterizes the system's ability to adapt itself towards changing environment. Adaptable systems deliver their intended functionality under varying operating conditions through changing themselves. That is, no changes from external have to be implemented into such systems to cope with changing environments.